in the absence of George, it's my pleasure to welcome you to the first series seminar of this semester. And it's my great pleasure to invite Professor Kazuo Hosomichi from YITP Kyoto. So Professor Hosomichi received his PhD from Tokyo University in 2001? 2000. And then after a series of postdoc, and he was briefly assistant professor in Korea Institute of Advanced Study. And since a few years ago, he has been an associate professor in Yukawa Institute, Kyoto, one of the best theoretical research institutions in the world. So Professor Hosomichi is a world expert in the topic of localization, supersymmetric gauge theory. And his work a few years ago has basically opened up a new field altogether in our kind of understanding of exact result in supersymmetric gauge theory. So it's our great pleasure to invite him to give us this seminar. Let's welcome.
Thank you very much for a nice introduction. And it's a great honor for me to be able to give a talk about my recent works. So today I would like to talk a little bit about my recent research on supersymmetric gauge theories, and about my about some of the exact results which was found by the application of localization principle.
Sorry, could you adjust the microphone a little bit closer to?
So my main message, the main message I would like to deliver today is that the localization principle. So this is based on classical mathematical theorem. This localization principle is actually a very powerful tool to study path integral of various supersymmetric quantum field theories. And in fact, indeed, recently there have been major technical breakthroughs in the mathematics of supersymmetric gauge theories by application of this localization. So in the first part of my talk, I would like to give you a brief explanation about what about this stuff. So these are the underlying principles which are very important. So first I would like to explain what the path integral is, and then what the localization principle is. And after that, I would like to give you how this localization principle has some relation to supersymmetry in quantum field theory. So these are the basic concepts underlying my recent research. And after going through all these concepts, in the later part of my talk, I would like to give you one specific example in which all these ideas have been applied to be able to find interesting exact formula about supersymmetric gauge field theory. Okay? So let me begin by briefly recalling what the path integral formalism is. Maybe all of you know, but nevertheless, still I would like to give you a review. So path integral is, as you know, one of the formalisms in defining quantum mechanics. So for example, we often consider a particle moving in a potential like this. And then if we are interested in classical mechanics, we are given this action integral, and from which we are instructed to derive the Euler-Lagrange equation. And then by solving it, we can determine the classical trajectory for a particle, right? But in quantum mechanical system, in quantum mechanics, what we have to do in computing the transition amplitude, for example, is to perform this kind of integral. Right? And this integral means we have to do the integral over many inequivalent trajectories like this. Okay? And we have to sum over all the possible different kind of trajectories with this integration rate, e to the is. And in particular, this integration measure dq expresses the fact that the q of t at each time instance t should be regarded as an integration value. So once we understand the definition of path integral, it's a really straightforward matter to generalize it to quantum field theory. So where instead of Q of t, we have phi of x. So phi is a quantum field, and x is a point on the space-time. So we are instructed to do an integration over the value of the quantum field phi at each space-time point. So this is the path integral formalism for a quantum field theory. Okay? And some of you may ask whether this integration over continuously infinitely many integration variable actually makes sense or not. But usually our standpoint is that we assume or admit that this is well defined and moreover satisfies a various nice property. For example, we can do partial integration whenever we want to do that. And then we can derive many useful formula, for example, the Feynman diagram or perturbation theory, or whenever this system has a continuous symmetry, we can derive the conservation of the associated current. Okay? But on the other hand, if this action functional is quadratic, or in other words, if the theory is free, we can actually try to perform this integral explicitly. Okay, if the theory is free, if the path integral is Gaussian, we can try to evaluate the path integral explicitly. So let me illustrate how to do that in the simplest example of a single harmonic oscillator. Maybe all of you have done this at least once. Okay, so let's try to compute this quantity, trace of e to the minus beta Hamiltonian. So all of you know what the spectrum is, so that this trace is given by a sum over energy levels. So this is a simple geometric series, so that you can immediately get the result. Right? This is 1 over twice the sine hyperbolic. Okay, so let's think about how to reproduce this using the path integral formalism. Have you ever done that? Okay, so in order to reproduce this, first of all, this is a time evolution along the imaginary time direction. So that we have to deal with the Euclidean action functional for this one. So this is the Euclidean action functional for a simple harmonic oscillator. And moreover, because we are interested in evaluating the trace, we have to introduce periodicity along the imaginary time, like this. Okay. Then, how to do the path integration over this periodic field? Well, since this quantum field phi is periodic, we can think about expanding it into the Fourier course. Okay. So, more attractable definition of the path integral measure is integral in terms of mode variable. Okay. So if you use the same mode variable, then this action functional can be rewritten into this form. So this you can do explicitly, not very complicated. And then after doing all this rewriting, you notice that the system of a single harmonic oscillator is just an infinitely many copy of Gaussian integral. Okay, so you can do the integration explicitly, and you get some infinite product. And after applying zeta function regularization on the resulting infinite product expression, you get precisely this answer. Okay, so in this way, you can reproduce what we know about the single harmonic oscillator from Hamiltonian approach using explicit path integral. So as long as the theory is free, we can try to do always this kind of stuff. But when the theory is interacting or non-Gaussian, then we can no longer hope, usually, to perform explicit path integration. So here, from here on, we need to work with approximation scheme. So there are various approximation schemes. But here, for example, let me draw attention to the saddle point method. So the saddle point method is one of the many known approximation schemes, so which we can use not only to the path integral problem, but also to various complicated integral problems. Okay. So what is this method? Suppose we have a path integral with this action functional, which have like this, several isolated local minima. Then the saddle point methods instruct us to perform the path integration over each of these saddle points under the Gaussian approximation. And then take the summation over the result. So this approximation scheme is known to be more and more reliable in the classical limit or in the limit where the Planck constant is approaching to zero. Okay? So whenever the theory is not Gaussian, we have to work with approximation schemes. But very surprisingly, recently, people got interested in the following property about the supersymmetric theories. In supersymmetric path integrals, actually the saddle point approximation becomes exact. And due to this remarkable property, recently there have been a big technical breakthrough in the path integral approach to the supersymmetric quantum field theories. So, and this remarkable property is phrased as the localization principle. And to be honest, my personal feeling is that despite the many interesting developments which took place recently, these are still somewhat far from application to the real particle phenomenology. But on the other hand, they are quite helpful in understanding many of the mathematical aspects in supersymmetric field theories. So for example, from purely theoretical or formal study of quantum field theory, we would like to know how to classify different kinds of quantum field theories in diverse dimensions, or we would like to develop the computational technique or computational scheme, and also we would like to obtain as many exactly computable quantity as possible, which will characterize different theories. So if we are interested in this respect, this recent development is very, very powerful tool. Okay, so this is the introduction, and in the next few transparency, I would like to explain what is the localization principle. But up to now, are there any questions?
Is localization principle applicable to the superstring theory?
Because superstring theory has space and supersymmetry. I think yes, but I think yes. But I have never thought about this. Yeah, so first I have to come up with interesting quantity which I would like to compute using localization principle. Yeah. And some of the example which I'm going to give you later is about the exactly computable quantity in gauge theory, supersymmetric gauge theory, and those theory can also be regarded as a part of superstring theory.
Well, it certainly can, right? I mean, there's topological string theory. There's some subset.
Oh yeah. Some version of.
But that's on the worksheet now in space-time. Space-time, you need to know what's the approach for all the degree of freedom, which is much harder.
Right. Other questions? No. Okay. So let me explain what the localization principle is. So I would like to try to explain it in as simple possible as simple terms as possible. So to do that, let me go back to again the most simple dynamical system of a single harmonic oscillator. But this time I use the canonical Hamiltonian forms. So to study this system, we have to provide with the symplectic form. So symplectic form for the single harmonic oscillator is dq/dp. And from this two form, we can get this anti-symmetric tensor with this element. So maybe some of you are not familiar with this formalism, but basically this matrix, the element of this matrix is roughly speaking the inverse, precisely the inverse of the Poisson bracket matrices. Okay? And also, in order to specify the dynamical system, we have to give the Hamiltonian. And for harmonic oscillator, Hamiltonian. is this. Then, if we are given this symplectic form and Hamiltonian, then they determine the motion in the phase space, as you know very well. And then the motion in the phase space is described by this velocity vector, which is nothing but the time derivative of the canonical coordinates. And they are given by the Poisson bracket of the coordinate with the Hamiltonian. And in terms of the quantities which I introduced in the previous slide, we can rewrite this thing like this. Okay, and in the case of single harmonic oscillator, the vector field V takes this form. Okay, so all is very fundamental and very easy. Right. So in this setting, let's consider the following integral. Z equals the integral over the phase space, and this is the volume element, and e to the minus h. So we are doing the integral of this quantity. So from one viewpoint, this quantity can be regarded as a regularized phase space volume. So naively, if we are interested in the volume of the phase space for a single harmonic oscillator, it's an integral of dq dt, so it's an infinity. But with an introduction of e to the minus h, one can make it fine. Another physical interpretation of this integral is a partition function for a very simple statistical mechanics at an inverse temperature, which is set to unity. Okay, so if for generic inverse temperature, we just insert beta here. Right, and then if we evaluate this integral for a single harmonic oscillator, again this is easy. Then we get, so this is simply Gaussian integral, so that we get this. Okay? So we can generalize the problem to many oscillators. It's straightforward. So the symplectic form is just a sum over n copies, and the Hamiltonian is also the sum over n copies. And for this problem also, we can try to evaluate the phase space volume with regularization. And this time the volume element is nth power of the symplectic form omega. And then again, the integral is Gaussian, so that the answer is this. Okay? Up to now, everything is elementary and very easy. Right. Then here comes a somewhat more interesting, mathematically interesting question. So suppose we are given arbitrary manifold with this symplectic form, which is closed to form, and this arbitrary Hamiltonian. Then can we compute the generalized phase space volume for the general choice of the symplectic form and Hamiltonian? So this looks like a non-trivial problem. Okay, so how to do this? Actually, in mathematics, there is a very powerful formula called the fixed points formula, known, and this formula is due to Duistermaat-Heckn. And this formula actually says that this generalized phase space volume can be computed as a sum over localized contribution from the fixed points. And by fixed points, I mean the zeros of the velocity vector, or equivalently the critical point of the Hamiltonian function. Okay, so the phase space volume is defined like this, and this can be evaluated as a sum over a fixed point contributions. So this is a remarkable formula. And moreover, if you want to evaluate this quantity E of P at each fixed point, you can try saddle point approximation about each fixed point, and actually the result that you get under the saddle point approximation is exact. So in more precise terms, what do I mean by this? Well, if I want to know what is the value E of P, all I need to know, all I need to do is to find a suitable local coordinate system near the fixed point P, so that the symplectic two form look like this, look like the one for n copies of harmonic oscillator, and similarly for the Hamiltonian. And then once I choose a suitable coordinate system which satisfies this, then we can apply the Gaussian approximation, and this is what we get. And actually, the localization, the fixed point formula tells us that this is the exact result. So this is really a remarkable formula. But you may ask, if this is true or not.
Excuse
So
me.
yes.
Do you need to take this small n, the summation n to be large?
Summation n to be large?
Yeah.
No.
You don't
So the
need to.
dimension is arbitrary.
It's arbitrary.
Yeah. Yeah, for arbitrary dimension, this local fixed point formula works.
But what kind of structure of your Hamiltonian needs to be? Here it's quadratic, right?
Yeah. So since I have since I focused to the vicinity of the critical point, that's why the Hamiltonian can be approximated by quadratic.
Plus a constant.
Yeah, plus constant. Yes, exactly. Yeah, right. So I would like to show you one example where this localization fixed point formula really works. So as an exercise, let's look at an integration over two spheres. Okay, and the theta and phi are the standard polar angle coordinates, right? And then in this on this sphere, let's put this symplectic 2 form, which is nothing but the volume form, right? And then let's also choose as Hamiltonian this function, which is also simple. Then, as I told you previously, once I choose omega and h, it defines the velocity vector. And in this case, the velocity vector v is just generating the rotation, fixing the north pole and south pole. Okay. Then for this system, let's try to compute the generalized phase space volume. And then if we want to apply the fixed point formula, then since we have two fixed points, then we will get the contribution from two fixed points, namely south pole and north pole. So this is how we can arrive at the result for the generalized phase space volume. But on the other hand, since the symplectic form and the Hamiltonian are both very simple, we can try to evaluate Z by brute force, and you can actually check that this the result which we can obtain by fixed point formula agrees with the result of brute force computation. Okay. So as we have seen, there is in mathematics there is a formula called the fixed point formula, which is very powerful. So at this point, any questions?
What does it have anything to do with supersymmetry? Because the volume integral, it's
Right.
going to be two
So-
form or some form.
Then you have to
Now, yeah, thank you for asking. So right now, from now on, I would like to explain why, how this fixed point formula is related to supersymmetry. Well, in order to understand why there is a relation, I have to explain some techniques. So first of all, we want to rewrite this volume element by introducing some fermions. So this volume element is a 2n-dimensional differential form, so that it has to be proportional to the product of dxi. And the proportionality factor is just the square root of the determinant. Okay? And then this determinant can be expressed as a Gaussian integral over some anti-commuting variable, so fermions, psi. Okay? So this is a rather well-known trick among field theorists, but I'm not sure whether this is, yeah, but anyway. Yeah, so this is the trick. And then by applying this trick, the generalized phase space volume can be rewritten in the form of 0 plus 0 dimensional quantum field theory. But actually, although I have written the integration measure like this, it's just a finite dimensional integral over 2n bosons and the 2n fermions. And the path integral rate is e to the minus s. S is the action functional, but this time S is the linear combination of Hamiltonian and something which is quadratic in the fermions. And what is interesting about this 0 plus 0 dimensional quantum field theory is that actually this system has a supersymmetry. and let's call the supercharge by Q. Then the Q transforms X into psi, and Q transforms psi into a function of X, Vi, which is nothing but the ith component of the velocity. Right. You may notice that the square of this supercharge Q gives rise to a symmetry generated by this velocity vector field V. Okay. So in some transparency back, I explained what the fixed point formula is, and then fixed point formula says that the non-zero value of the integral localizes onto the fixed point, which is characterized by the vanishing of this velocity vector field. So in turn, in this supersymmetric setting, this vanishing of the velocity vector fields can be rephrased as the vanishing of the supersymmetric variation of all the fermions. Okay. So from this observation, I can motivate the localization principle in supersymmetric quantum fields. Okay. So this localization principle consists of two principles. The first one says that the path integral of supersymmetric quantum field theories localize onto saddle points, and the definition of the saddle points is that the supersymmetric variation of all the fermions is vanishing. Okay, so this gives you a tremendous simplification from infinite dimensional half integral down to some finite dimensional integral, typically. And the second statement is that the contribution of each saddle point can be evaluated exactly by Gaussian approximation. So recently, this localization principle have been applied to many interesting calculations in supersymmetric gauge theories. Right. So among many recent developments, I would like to give you one example, which is a four-dimensional n=2 supersymmetric theories. So right now, are there any questions?
Could you go back to the previous transparency?
Okay.
So what the statement inside the box, is that a unique choice? Is that just a choice or the choice? I mean, the Q of fermion is vanishing.
Right. So we have to consider the space of all the bosons and fermions, and we have to look for all the points, and somewhere in that space, there are points satisfying this.
I know, but in your zero-dimensional example, Q to psi is V, right?
Q psi is V, yes.
So V is 0 is the critical, the central point.
Yeah.
So you need to find a theories.
Yeah, for which.
But I mean, this is not the usual definition of supersymmetric transformation in the usual SUSY, right? Or is it?
In the usual
Oh, I'm
SUSY
sorry.
means,
So you say the central point is.
maybe in later some later transparency, I would like to talk a little bit about usual supersymmetry. Maybe usual supersymmetry. By usual supersymmetry, you mean the supersymmetry which generalizes the Poincare symmetry. No? Are you a particular theorist? Or?
I mean, okay. The usual statement is that Q of psi is something, right? Mm-hmm. Okay, and that something is to be set to 0 defines the central point. Is that what you say?
Yeah.
And this is good for any
Yes.
SUSY, right?
Yes.
But why the four-dimensional n=2?
So there are many examples in which this localization principle actually works, and we were able to obtain many interesting exact formula. But among those many developments, I want to focus on particular examples.
Right. Suppose let's look at a simpler SUSY model, like just the way to minor model. Then what? I mean the supersymmetric way to minor model.